I'm using the capability of LT Spice here, okay? I don't have to write down, calculate those numbers and write them down here as like 2.3 or 9 or, I don't have to write that. I can just write exactly the expressions that I derived for A2, A1, E0, B2, B0. TS is defined as 100 microseconds, right? So once I know TS, all these numbers down here are known. They're known. So I can use them in my circuit elsewhere. Now, what I have done here, which doesn't exist in LT Spice as we see it, I defined something called a unit delay. I made that block. Okay? And what's in it is this. That's what's in that block. And I used behavioralist voltage source. Wow, I never saw a voltage source this big. Must be a very large value, right? What does this thing do? Well, when the input is applied here, there's a voltage here. And this is very large resistance, so it doesn't load down anything, right? We take that voltage V in, and it delays it by TS. There's a function called delay that's in LT Spice. And you can use it this way. It takes the thing and delays it by that many seconds. And what's this value TS? It's not defined here. It's not defined on this sheet. But if you go to the top level, here, it's being passed in. So what I just showed is a subroutine. It's really a subroutine. It's a sub-circuit. But it's really a subroutine. And I'm passing into it the value of TS. So it says TS equals curly TS. So I could have called it anything. Curly means compute the value of variable called TS. So that's what it means. So that will pass in that value to every single block there. And the other thing I've done here is that I made this test sine wave source, and I have these two things that actually do the sampling. These are sample and holds. They sample and hold. That's the name, sample and hold. Okay? And these are actually built into LT Spice, but they're undocumented. So you can't find them unless you know where to look for it. But this, all this thing does is basically input is this, input to this block is a sine wave, and you also feed it into a clock, right? So every time the clock goes high, the output xk in this case gets latched to the inputs. So what you end up getting, if you give like a sine wave, you get these staircase sample and holds. There's also a way to feed the clock to the sh input, in which case it'll do a first order sample and hold. This is like a zeroth order sample. So this one will follow the input when the clock is high. Either way, xk is a sample version of this voltage Vn. And then here we go. Here are these two xk1 and xk2, right? And here's my yk. And here's my yk1, yk2, it's two-way versions. And the voltage here at yk is equal to this expression. And that's exactly the expression I wrote down. But I'm not writing just yk, I'm writing V at yk1, right? Because remember, this is a simulator, these are voltages, right? So this point here is yk, this point is yk minus 1, yk minus 2. So the V gets the variable from there. And now the value at yk is this. So even though there seems to be no connections, like I drew on the signal flow graph, these things are connected because whenever I say xk1, xk2, or I say V and xk, there's an invisible connection from here to that point. And if I want to, I can just draw a wire from here and make all kinds of additions, but this is clean. Okay, so basically what I'm saying here is that if I put in a sine wave at 20 hertz, that's right at the corner frequency. My Bode plot is telling me that I should have exactly 0 dB. It should go out as a sine wave. But in reality, it's smooth, right? Our transfer function is smooth, and we're going to be off by 3 dB. So we're going to get reduction by 3 dB. In other words, I expect 0.707 as the amplitude, not 1. So let's just run it to see what happens. Okay? So we're going to run it for 100 milliseconds. We can run it for 200 milliseconds of delay. We have to run it enough times so that we can see something with the period, right? So we run it. And so here is VXK. This is the sample version of the inputs. It's a 1 volt, 20 hertz sine wave. And here's the output. This is VYK. Okay? This is actually sampled. So in reality, I mean, there is a smooth version of that, right? And there will be a smooth version of this. But I'm just showing the sample versions, right? So like if I went to V in, like this thing right here, this is V in. This is the smooth version, an analog version of it. Let's compare it. Okay? It's right on top of it. If you zoom in, you'll see the thing, right? The red one is the actual analog sine wave. The blue one, or whatever that color is, okay, is the sample version of it. After the sample, that's X of K. The blue one is the one that's going into our digital filter. That's being processed. And out comes this. Down here, that's VYK. I don't have DOT, right? I don't have the unsampled version of the output, but this is basically the output. And if you look at it, you know, it does look like a sine wave, and it is 20 hertz. You can go from here to here, and you will see 20 hertz. How do I do that? If you just use the cursor here, left mouse button down and just drag, don't release. Just drag like this. If you look down in the corner there, you will see the time difference, and you will also see the frequency measurement, 1 over. You see it's 20 hertz, right? So that's how you can make quickly a measurement without putting the cursor on. Okay, and the peak, you can see right here, the peak is right around here. It's about 0.7 or something. I'm good. Okay, I don't worry about the third digit. So this is doing the right thing. If I do this at 20 kilohertz, I expect the same thing. I expect the amplitude to be reduced, right? If I think even a higher frequency, the attenuation should be more and more and more, according to that curve. That curve is telling me what the attenuation or the gain is. The reduction or the gain. Right? So if I pick, I think I'll pick some other frequency. For example, I can pick something right in the band. Okay, let me pick, I don't know, like 300 hertz, right? That's closer. That should go through as is, right? If I put in 1 sine 200t or 300t, okay, I mean that should go with a magnitude of 1. Okay, so far we've been doing the filters I'll get rid of this one. We're doing the filters in the frequency domain, but in time domain you can do it too. You can put in a signal and see how it attenuates the frequency. Change the frequency, see the amplitude, right? So let this one go and see what happens. Now this one, because I increased the frequency by about 10, I don't have to simulate as long, so I'll go only up to 20 million. This is just to conserve time, okay? Like this, and it's simulating pretty quickly, and you can see, in the beginning there's a little bit of a transient, but after a while it reaches steady state, and you can see it's 1 and minus 1, right? Because this is in the pass band. This frequency is in the pass band. Therefore, the name band passes, right? It passes that band, okay? Et cetera, et cetera. So you can put in different frequencies and see what it does. So this thing is doing that filter. Now, not only that, a lot of times when you're implement this on a microcontroller, you'll be wanting to know what these values are. These things that are multiplying the different present and past values that are sitting in a register that needs to multiply and add and so on. So you need to know what this coefficient and what this coefficient and that coefficient is. And so you can actually do what's called a measure command, another command that you might not know about, but it's in the slide. I can actually measure these values, right? Because these values are not printed, right? What are these coefficient values? It didn't print it, right? But actually, if you use the measure command, it appears at the splice output. So it actually did that for me already. All I do is view the error log, and it's sitting right there, right? So the A2, A1, A0 variables are right there. Those are the numbers, and the ratios, which are A0, A1, etc., are down there. So you can see those coefficients are less than 1. So you could take this information and go to the next step, right? So it's not bad. Okay, so just because we're doing analog doesn't mean we can't do digital too. In fact, I claim we might be able to do better digital than digital. But you can go this discrete time. Okay?